everyone. I'm going to talk today about some recent modeling I've done of LNG fires. I'll first provide a little bit of background on this. I was contacted about a year ago by Lukita, who works at Sandia National Labs, which is a Department of Energy facility in Albuquerque, New Mexico. And she had been asked by the Pipeline and Hazardous Materials Safety Administration of the U.S. Department of Transportation to do what's called an MEP, a Model Evaluation Protocol for LNG fires. Now, an MEP is really a set of guidelines that modelers would use if they wanted to demonstrate that their model is appropriate for a particular application. So in this case, suppose that one of you wanted to use FDS to do an analysis of fires at an LNG facility. The authority might want to know more about the model and how it performs for these kinds of calculations. So you follow the guidelines in the MEP. A big part of the MEP is the experiments that you see listed here. So these are experiments that were conducted over the past 40 years, all involve LNG. There are some trench fires, pool fires, fireballs, and jet fires. And I've simulated them all with FDS and put the results into the FDS validation guide so that any of you who want to do this sort of thing, not necessarily for the United States authorities, but wherever you are, you have some starting point to talk about how well FDS can simulate these kinds of fires. Before I get going, let me acknowledge Lukita at Sandia for doing a lot of the work. She set up all the FDS calculations originally. She dug up all these old test reports and poured through reams and reams of data to put this together. And she is the author of the report. It is, as all of you know who's ever done validation work, it is a tremendous task to organize all this material, especially when it's 40 years old. And you'll see from some of these documents that I'm showing that this work was really pulled out of mothballs. Okay, so I'll start by going back in time 40 years to look at some experiments that were conducted by Croce, Moudin, and Morehouse on behalf of the British Gas Corporation and the Gas Research Institute. For any of you who have had a background in fire science, and especially big pool fires, these names should sound familiar to you. You'll see them in the SFBE handbook. They developed a lot of the empirical correlations that are still used today for evaluating the hazard from large outdoor fires. So in these experiments, there's a trench, and shown here in this picture, if I can bring up the pointer, okay. So we have this trench. The trench is flexible, so it can be changed in size for the different tests. It's about 50 meters long and some 30 meters wide, but these dimensions will change from test to test. Okay, the FDS simulations of these experiments were fairly straightforward to set up. You have a rectangular pool. You have the trench is filled with liquefied natural gas at a certain temperature. You're given the burning rate, and you position in the vicinity of this fire radiometers, both in the downwind direction, in the upwind direction, and in the lateral direction. And shown here at the top right are some predictions of the heat flux to these distant radiometers. The experiments are shown as circles and the FDS predictions are shown as lines. And as you would expect, you see the heat flux decreasing as you get further away from the fire. You also notice that the downwind radiometers show slightly higher heat fluxes than the upwind radiometers, as you would expect, because the fire is tilting towards the downwind radiometers. Okay, next up is another set of experiments from the 1980s known as the Montour LNG fires. And these were three 35-meter LNG pool fires conducted by a consortium of British and French petroleum companies and gas companies. They were done at the Montour de Bretagne methane terminal on the coast of France. You can see some crude photographs on this slide. Unfortunately, a lot of the original photographs have been lost, at least we could not find them. Here's a sketch of the facility showing the fire in the center, and then as before, we have radiometers arrayed in radial locations. Okay, here on this slide, I'm showing some FDS results, like the ones I showed for the previous set of experiments. And more importantly here, I'm showing this funny looking plot of what's known as the integrated intensity. So one of the big issues that you have to keep in mind when you're doing these kinds of simulations, where you have a fire surrounded by heat flux gauges or radiometers in the far field, these are challenging because the FDS radiation solver discretizes the radiation heat flux into essentially discrete bands or directions. So imagine if you took the unit sphere, by default we divide the unit sphere up into 100 solid angles. And the further away from the hot stuff you go, the more obvious it becomes that you have discretized the radiation field into these 100 angles. So oftentimes when you're doing calculations like this, you have to increase the number of angles. And how do you know how much to increase them by? Well, in this case, what I did is I created this horizontal slice of the integrated intensity at the ground or near the ground where the radiometers are. And by looking at the pattern, I can tell when the star pattern becomes intolerable. In other words, suppose my radiometer were at this point here. You can see that the radiation heat flux at this point is going to be relatively low to the radiation heat flux at this point, just a little bit of distance away. Well, that shouldn't be the case. In reality, the radiation is going to be the same at this same distance from the fire. But because of the discrete bands that we're using, or I'm sorry, I shouldn't say bands, the discrete directions that we're using in FDS, you'll see that the radiation flux field is not uniform here. So you have to use more angles to cover the field. The other thing that you'll notice, let me see if I can start the animation again. The other thing that you notice here is that you can see quite clearly that I have divided the computational domain up into, I forget exactly how many, about 80 meshes. And the radiation field is updated on those meshes individually, and it takes time for the radiation field to sort of come together in a coherent way. Now, in these cases, I'm looking at the steady state heat flux at these points, so I'm able to get away with a little bit of distortion in the radiation field, because when I time average it, that distortion goes away. But it's just something to be aware of, and again, I use the integrated intensity as a good indicator of whether or not I'm resolving the radiation heat flux appropriately at a given distance. Okay, we're moving into the 2000s now, and we actually have color photographs of these experiments. These are some fireball experiments that were conducted by Shell Research in the UK. And what we have here are experiments in which liquefied natural gas is stored in a containment vessel, shown here at the lower left. And the vessel is ripped open with explosive charges, and all of the LNG spills onto the ground and is ignited with fireworks, and that creates a huge fireball. Now, there were 4 experiments conducted. We chose to simulate the last 3, 2, 3, and 4, they're called. In each one of these experiments, they used the same type of containment vessel, but with different amounts of LNG, going from 681 all the way up to 1251 kilograms. So this is a very large amount of liquefied natural gas that is spilled out rapidly onto the ground and ignited. From a modeling standpoint, these calculations are fairly easy to set up, and I guess it's easy because there's really not a lot that we know about what's going on in the vicinity of the ruptured vessel. All we really know is that we have a large amount of cold liquid that is rapidly vaporized and creates a fireball. So in the FDS simulation, I create a vent at the ground that's comparable to the size of the containment vessel. And in roughly 1 second, I push all of the mass of the fuel through this vent, and then FDS creates the fireball that you saw animated. In the experiments, they had radiometers in the far field that would capture the heat flux for roughly 10 seconds or so. You can see the plot shown here, experiment 2, 3, and 4. In experiments 2 and 3, we only have data at 100 meters from the source. For experiment 4, we actually have some data that's closer in. A lot of this data is either unavailable or is still proprietary, so we're only able to extract a small amount of it. But nevertheless, it does indicate that the model is doing a reasonably good job of predicting the peak heat flux to these distant targets. I think one of the challenges is to get the time sequence right. You can see, for example, in experiment 2 that in the experiment, the peak heat flux occurs at about 2 seconds after the detonation, whereas in the model it's 4 seconds. Again, these details of what's going on right at the start are very hard for the model to capture. So I'm actually kind of pleased that we got these results without really fussing too much with a lot of empirical parameters. Okay. Now we're going to look at another set of pool fire experiments. These experiments were conducted at Sandia Labs in Albuquerque, New Mexico. And for any one of you who have ever been to New Mexico, a lot of the state is a desert, and so Sandia has many large-scale facilities spread out over a very large land area. This is one of their big fire facilities shown here. They basically have a pool of water that's 120 meters in diameter, and they have a storage tank of LNG, and they would dump the LNG onto the water very rapidly. And in the two experiments that we looked at, one was 21 meters in diameter and the other was 83 meters in diameter. Here's a photograph of the 83 meter diameter LNG fire. You can see that the flame height goes up to about 200 meters. Okay, I'm showing the FDS simulation of the 83 meter diameter fire here. This is a very large computational domain, and I've cheated a little bit to save on computational time, and that is I've put a grid over the fire, and then I have created meshes off in the 4 directions to capture the locations of the radiometers. If you do this sort of thing, you want to make sure that each of your radiometers can see, quote unquote, see the entire fire. You do not want to cut off the view from the radiometer to the fire in trying to save on a little computational time. The plots that I'm showing here are typical or similar to what I've shown before, where you have heat flux at a distance. One of the remarkable things here is that if you look closely at this plot here in the upper right for test 2, this is the larger of the 2 fires. I mean, we see that we have heat fluxes on the order of 20 to 30 kilowatts per meter squared, a distance of 100 meters away from this fire. So that gives you an idea of how large this fire is when you're 100 meters away and you're still seeing heat fluxes that would ignite a piece of paper. And while I'm on that subject of distance, another thing to keep in mind when you do these calculations, and I talk more about it in the paper, but I'll mention it here. When you have these large fires outside of a building and you're looking at heat fluxes, you have to account for the fact that the water and to some extent the carbon dioxide in the air that occurs naturally is going to absorb some of the radiation from the fire. So you want to account for that in your calculation, and FDS does account for that. It does do a radiation absorption calculation as part of its solution of the radiative transport equation. However, you have to pay attention to these large distances because there's a parameter that most people never really have to fuss with called path length. And it's a parameter that's associated with the radiation solver. And what the path length is the distance over which the absorption coefficient for the radiation solver is calculated. Now, by default, that distance is 10 centimeters. So when we come up with an effective absorption coefficient for what we call the gray gas, which is independent of wavelength, we use 10 centimeters as a path length for that calculation. Now, that's fine, we have found for compartment fires, but when you're dealing with these large distances, and this domain here is about 500 meters, actually it's about 250 meters from the fire to the radiometer, so this is about 500 meters across. The 10 centimeter path length that we use is not appropriate. So if you look at the input file for these cases, you'll see that the path length has been set to something like 250 or 300 meters. That means that the absorption coefficient for water and CO2 and the other gases has been calculated based on an assumed travel distance of 200 or 300 meters, not 10 centimeters. And again, I talked a little bit more about this in the paper, but it's very important, because if you don't set this path length to be a large number comparable to the size of the domain, you can have the water vapor in the air actually absorb far more radiation than it would naturally. Okay, for the next set of experiments, we're back at Sandia National Labs in Albuquerque. They have another facility known as the FLAME facility, or the Fire Laboratory for Accreditation of Models and Experiments. And what this is a very large cylindrical enclosure with a hood at the top for drawing out exhaust products from a fire. And you'll see here on the floor of the facility is a 3-meter diameter hole. And in this case, methane is pumped into the basement of the facility, and it comes up through the hole in the floor and ignited. Okay, here are some animations of one of the experiments. They actually conducted 28 of these experiments with fires of different sizes. And the objective was to measure the flame heights, temperatures within the plume, and the heat flux to radiometers that were about 9 meters away from the fire. Now, they used two types of heat flux gauges, a wide-angle heat flux gauge and a narrow-angle heat flux gauge. And you can see the results for a couple of experiments in the upper right corner. Now, the wide-angle heat flux gauge is the one that you're all accustomed to. It's one that has more or less the full field of view. Okay, so that's whenever you go into a lab and you're measuring heat flux, that's typically a wide-angle gauge. The narrow-angle gauge is designed to be aimed directly at the flames, and what it does is it measures the radiation heat flux that is emanating from the flame without seeing all the background. Okay, so if you only want to know, okay, what is the heat flux coming right off that flame, you use one of these narrow-angle radiometers. Now, in FDS, the way we mimic a narrow-angle radiometer is, I talked before about the discrete directions that we transport radiation. So when we want to know what the narrow-angle heat flux is, we choose one of those closest to the target, and we only use that to assess the radiation heat flux. In other words, we're not looking at the heat flux coming from cold, distant sources. We're only looking at the heat flux coming directly from the fire and going to the target. Now again, I'll mention here, and you can see evidence of it on the plots. If you look at this animation that I'm showing in the lower left, this again is the integrated intensity. And you can see that when you get about 9 meters away from the fire, you can see the star pattern develop. And you'll see that star pattern manifested in the FDS prediction of the heat flux at about that distance. So you see here that as a function of height, 9 meters away from the fire, the heat flux is roughly 1 kilowatt per meter squared. You can see that the experimental measurement is relatively smooth, but you can see the evidence of the star pattern in the FDS prediction. If I wanted to eliminate that star pattern, I would have to use more angles, or another alternative is that I could spatially average the heat flux over a couple of grid cells, which would tend to reduce the variation. Here you can see the narrow angle heat flux for this experiment. And you can see that the narrow angle heat flux is 10 to 20 to 30 kilowatts per meter squared from this distance. And again, that's because if you only look at the flame and you ignore all of the surroundings, you'll see that higher heat flux. Okay, the last set of experiments I'm going to talk about, I call the Loughborough jet fire experiments. Loughborough is the name of a university in the UK, and some researchers at that university supervised and did the analysis for these experiments. So what you see here is a pipe with liquefied natural gas. That pipe has a small orifice at the end, and the gas is pushed through the orifice at very high pressure, forming a jet fire, which impinges on a cylindrical target. You can think of this as a pipe or something like that. And the objective of the experiments is to measure the heat flux from the jet fire to this target. Okay, so here's the FDS simulation of these experiments. Now, this is a difficult calculation to perform because FDS does not do supersonic flow. And in this case, the flow coming out of that orifice is supersonic. So the way we get around that is we use liquid droplets which are projected at high speeds from a certain point and given a small spray angle, I think something on the order of 10 degrees. And these droplets are initially at low temperature, but they have the properties of liquid methane, and they vaporize rapidly and burn, and you get the jet pattern that you see here. The pipe is modeled as a series of rectangular obstructions. Again, that's another big approximation that we have to make. And we are recording in our simulation the heat flux from the jet fire to different points along the perimeter of the pipe. So in the plots at the left, we show heat fluxes to the top, to the front, to the bottom, and to the back of the pipe. Now, the error in these simulations is pretty substantial because the heat flux to the cylinder is pretty substantial. Where FDS is poorest is at the back. So behind the obstruction, they're measuring heat fluxes that go up to about 400 kilowatts per meter squared. And in the model, we're just not capturing the behavior of the hot gases and the combustion in the wake of this cylinder. And in some sense, that's not surprising because we're not really modeling this as a cylinder. It's being modeled as kind of a Lego block collection of rectangular obstructions. And so if we wanted to do a better job of looking at the heat flux to the back, I think we'd have to have much higher spatial resolution and much more detail given to the obstruction. And for these calculations, we just didn't have the computational horsepower to capture both the details of the pipe and the entire jet. But nevertheless, we can assess, where the model is able to predict reasonably well the heat fluxes and where it can't. Okay, I'll finish up the presentation with a few of the scatter plots summarizing the results of these simulations. And by the way, all of these results that I've shown and more are in the FDS validation guide. I've only shown a handful of results just to give you a sense of where the model is predicting well and where it's not predicting well. This plot here is showing the results of the flame height calculations for 5 of the 6 experiments. You can see that the model is over-predicting by about 30%, largely due to the Sandia methane burner experiments. Okay, most of the data that we looked at was heat flux data to these targets surrounding the fire. And this busy plot shows the results of all 6 experiments. Just a quick look shows that these Loughborough jet fire experiments that I just presented are probably have the most scatter associated with them, especially at the high end where you have heat fluxes of 300 and 400 kilowatts per meter squared. And then you can also see that there's quite a bit of scatter at the low end when you're down to heat fluxes of 1 kilowatt per meter squared and lower than that. So that's when you're hundreds of meters away from one of these fires, and you might predict, you know, a heat flux of 1 kilowatt per meter squared, and the measurement is half a kilowatt per meter squared, and that's, you know, 100% error. So it's not surprising that we see that most of our error or large errors are coming at the high end and at the low end. But this gives you a kind of a sense of how all the different simulations are performing relative to each other. Okay, that is all I have to present. As I said before, all of these calculations are included in the FDS validation guide, so you can study more about them there. In the paper, I've talked a little bit about some of the numerical techniques that were used to simulate these fires, and the validation guide also contains some more information along those lines. So thank you for listening, and have a good day. Hello, everyone.
Okay, we'll check mic check level here. Let me pull this one down. Hello, check. Okay, let me switch over here and we'll get Kevin on the line. Ooh. Hey, Kevin. Ooh.
Kevin's here.
All right, hey. There we go. Let me switch you up here. Whoop. We've got, look at this. I can control it with my mind. Or Eric. All right, so let's switch here, and I'll full screen you. Yeah? Okay, great. So I'd encourage everybody, even though you're in the room, if you can go to the Hop-In app, if you go to the Event tab, there's a Q&A and a chat. Some of you have already been talking, but if you go to the Q&A and ask your questions through here, we'll be monitoring the app here, and we can ask the questions of the speakers. And then we can also just do live. Kyle will have a microphone if you have any questions for Kevin, and I'll have to repeat those. So you hear me okay, Kevin?
Yeah, I'm here.
Good morning.
Good morning.
Thanks for waking up and doing this for us today. Any questions here in the audience before we get started? Don't make Kevin wake up at 4 a.m. for no reason. Somebody has to ask a question. Okay, we did have questions earlier. I think Barbaro asked, and then it's been removed, so it may have been answered in your talk. But do you know of any larger scale BLEVE experiments that were used that than the ones that you presented here that have been processed yet or not?
No, and in fact, a lot of the credit goes to Ane Lukita of Sandia National Labs. She's the one who, dug through the archives to find these experiments. And you can see that a lot of them were done in the 80s and 90s, especially in the UK and in France when, there was a lot of exploration in the North Sea. Mm-hmm. So that a lot of these tests were kind of associated with that, the drilling that was going on in the North Sea at that time. But since then, there hasn't been, as much work in this area. It's almost like, large pool fires. I mean, there's a lot in the literature about them. There was a lot of work done, and now a lot of the simple methods of calculating, heat flux from large fires is fairly well understood in the handbooks.
Mm-hmm.
But we saw this as a great opportunity to do some, model validation work.
And are there any additional data sets that you're looking at to bring into the validation suite?
Yeah, so this was all LNG, and now what they're doing is they're looking for other fuels. For example, what is it? LPG, liquified propane gas, and some various other, flammable liquids and gases that you would find in these facilities. So LNG is where they started, but they're continuing doing work on other gases. From a modeling point of view, the other gases aren't that much different. I mean, there's different, radiative heat fluxes from the sootier fuels, but they're all kind of similar. So we're still digging through the history and looking for the LPG. And Ine and I will be, putting those together and putting them into the guide over the next year or so.
And in terms of like flame spread through the vapor cloud, are you seeing anything in the physics of that with that sort of deflagration, propagation speed, and how FDS is capturing that?
Actually, I mean, believe it or not, we're just using the default combustion model to do these calculations. So the default combustion model is a mixing time model, basically. And there is, it's all dependent on the grid size. And so when your grid size is like, 1 meter or several meters on a side, the mixing time is also, relatively large compared to, say, a small scale calculation. And, we were surprised. We didn't have to really fuss with the basic default settings, which is good, because you don't want to have to do that for these cases, because it's really hard to know exactly what's going on within that big fireball. But no, it was just done with the regular settings.
There is a question here too that says, when the solid angles are less, like around 100, the intensity to the far field is fluctuating with the star pattern, I think that you said.
Yep.
They're asking for some elaboration on that. I think there's some decent information in the guide about the angles and the effect of that star pattern, and I think in the verification as well. Is there anything else you'd want to add about the, I know there's like the horizontal angles and then the polar angles, and there's some different, I suppose it depends on the directionality of the targets and like where they are relative to the source, but is there anything else you want to add about that?
Simo Hostika of Finland is the one to blame for all this. No, actually, he's the one who gets the credit for it. And so if you look in the guide, you'll see, the unit sphere and how it's divided. One thing to keep in mind, in addition to, keeping in mind the star pattern, also the radiation angles do not align with the coordinate axes. In other words, if you take the unit sphere, the number of angles you put into FDS is rounded off so that you actually have an equal number of angles in each of the 8 quadrants of the unit sphere. And that means that you want to avoid putting your target right along the axis. Now, I know when you set up your calculation, that's the most normal thing to do, right? If you put the fire right at 0, 0, then you're going to want to put these radiometers, on the x-axis or on the y-axis. But that's actually not a great way to do it, because then you're at a trough, like a low point in this star pattern. So what I often do is I often rotate the experiment by, 10 degrees, 20 degrees, whatever, so that I don't align myself with the coordinate axis. And that's just an issue having to do with where we decided to, or how we decided to divide the unit sphere. So it's always good to draw that star pattern using slice files, both horizontally and vertically, and just first of all, make sure you've got enough angles to give yourself a decent distribution in the far field, but then also try to avoid being directly on a coordinate axis.
Okay.
You do a little trigonometry to put yourself a little bit off the coordinate axis.
And you did mention the spatial averaging as well in that field.
Yes.
And so that could average out a bit the difference in that, depending on your distance from the target.
Yeah, so I've noticed a number of people will just use a handful of radiometers that represent one and just kind of distribute them over, however many meters, just to make sure that you're not accidentally putting yourself into a hot spot or a cold spot.
Mm-hmm. Mm-hmm. Okay, another question here. How is the mesh cell size chosen for those? And is that described a bit more in the paper that is available or in the experimental information?
It's probably not described in the paper. I think we just did, a grid resolution study. With each of these cases, what you're probably seeing is the middle resolution. So we did it at, one level coarser, one level finer, and we didn't see that much difference in the results. And it makes sense for these large fires. If you're specifying the radiant fraction and you have the heat release rate, specified as well, as long as you deal with the star pattern, you're going to get a decent result. Mm-hmm. And one way to check that you're getting that decent result is just to fall back to the point source methodology. That is, if you're far enough away from the fire and you know its heat release rate and you know how much energy is radiating, what fraction of the energy is radiating, just calculate radiative fraction times the heat release rate divided by 4 pi r squared, mm-hmm. where r is the distance from the target to the center, that we call the point source method, mm-hmm. and you should be in the ballpark.
Mm-hmm. It's a good way to use the hand calc to verify your...
Use the hand calc just to double check. Yeah. I think that a lot of times, using CFD for these might not be necessary if you're far enough away. I think the CFD becomes more important if you've got things like wind or geometric obstructions between the fire and the target. Mm-hmm. But if you just got a fire out in the middle of the open and there's not a lot of wind, then the point source radiation will work, reasonably well. And there are also empirical methods that are a little bit more accurate than the point source that could be used. It's, CFD is typically used when you've got a much more complicated geometry.
Right. And it says, can we now use the current version of FDS to directly simulate high pressure liquefied flame of LNG? I'm assuming the last set of experiments with the jet fire and is that
these were all done with the latest version. So you can check through the validation guide for some of the notes that I've written up on each of the experiments. And the paper also provides a few of the things you need to look out for when you put the input file together. I think of all of these experiments, the jet fires are still the most challenging because you're dealing with supersonic speeds coming out of a tiny little hole. And again, in the model, we're kind of faking the supersonic part of it, mm-hmm. using these liquid droplets at high velocity. But it's still a challenge in terms of numerical stability and the physics of that near field phenomena.
Mm-hmm. Mm-hmm. Any other questions in the audience? I don't see anybody jumping up with their hand waving in the air. So
it's early for them too.
Yeah, we're just getting our coffee here. Maybe in another hour we'll all be ready. Okay, I think that one comment I just noticed here was it's kind of also nice to look at boundary radiant faces. So look at the boundary and the radiant profile on the surfaces if you have those as targets to see that pattern as well, not just in the integrated intensity. So you can see those hot spots and cold spots.
Yeah, I think a lot of people misinterpret what radiative intensity is. It's not the actual heat flux that you would feel if you were standing there. It's more of an integrated average, but it does provide you with a good way of checking whether your radiation calculation is well resolved or not. So
Yeah.
I always add that to my calculations where I'm looking at, heat fluxes to distant sources.
And one thing I've used in the past is using the 3D slice of integrated intensity, and you get like a 3D object that you can, this volumetric sort of field of intensity, which gives you a nice shape, and you can evaluate your objects in that volume instead of just the slice, 2D slice.
Okay, yeah, that's a good idea.
Yeah, it's an interesting way to look at it. So,
yeah.
Anything else? We good to transition? Okay. All right, well, thank you so much, Kevin. Appreciate your time and everything and connecting with us today. And we'll see you later from Brno.
Yeah, I'll be around. I'm planning, I'm already up, so I'll be watching the talks.
Well, so I would say Q&A is good for the current speaker. If you have just general comments or things, you can use the chat for that. And just speakers and everybody might be keeping an eye on the chats and saying hello there. So, okay, good. Thanks, Kevin. We'll see you later.
All right. Yep.